Good morning, class. We are looking at exam 3 review, covering chapter 3, differential rules, chapter 4, application of differentiations. Here's section 4.2, the mean value theorem, and 4.3, how derivatives affect the shape of a graph. 4.2, the mean value theorem, starting with the Rolle's theorem. Let f be a function that satisfies, number one, f is a continuous function on the closed interval of a to b. F is differentiable on the open interval of a to b. And finally, f of a equals f of b. And then there is a number c in the interval of a to b such that f prime of c equals 0. If you look at all these graphs of some typical functions that satisfy the three hypotheses. So we have continuous and differentiable. A curve which is smooth is also differentiable, okay? So in all cases, when f of a equals f of b, then there has to be a point where f prime is 0. In other words, there has to be a point that you can draw a tangent line that is horizontal. In each case, it appears that there is at least one point with coordinates c comma f of c on the graph where the tangent is horizontal, and therefore f prime of c equals 0. So, as an example, let f of x be x to the power of 4 minus 2x squared. Find all c in the interval of -2 to 2 such that f prime of x equals 0. And reminding you of Rolle's theorem, continuity, differentiability, f of a being equal to f of b. So what we are dealing with, obviously, it's a polynomial of degree 4, which makes it continuous and differentiable from negative to positive infinity. So this function is continuous and differentiable from negative to positive infinity. Therefore, it's continuous in the closed interval of -2 to 2 and differentiable in the open interval of -2 to 2. So we got the first one, the second one. Let's go to the third one. Let's look at f of a as well as f of b to check if they are equal. So f of a means f of -2. So we're going to plug in -2 to the power of 4 minus 2 times -2 squared. This is 16. This is 4. 16 minus 8 is 8. Now, if I plug in 2, also I get 8. So f is continuous, f is differentiable, f of a equals f of b. There must be a point such that f prime of c equal to 0. How do you find that? You differentiate this and set it equal to 0. So f prime of x is 4x cubed minus 4x. You set it equal to 0. So factor the 4x out. You get x squared minus 1. You said this one equal to 0, x is 0. You said this one equal to 0, x squared equals 1. X is plus minus 1. So there are 3 points. Thus, in the interval of -2 to 2, the derivative is 0 at each of these 3 x values, -1, 0, and 1. So if we were to look at the graph of f of x equals x to the power of 4 minus 2x squared looks like this. When f of -2 is 8, so is f of 2. Of course, a polynomial of degree 4, smooth, curve, continuous, and differentiable. So this point, and this point. At this point, this is the tangent line. at this point. This is the tangent line. All three are horizontal, and the slope is 0. Let f be a function that satisfies f is continuous on the closed interval of a to b. So the first criterion that was used is used here. The second one also. F is differentiable on the open interval of a to b, but not the third one for the Rolle's theorem. So then there is a number c in a comma b, in the interval of a comma b, such that f prime of c equals f of b minus f of a, f of b minus f of a over b minus a. So what does it mean? So you have some sort of a curve, smooth curve. So obviously continuous. And because it's a smooth curve, it's differentiable as well. What we are saying is, if we look at, for example, these two endpoints at A and B, and if we connect them, that gives us a line. The name is a secant line. What we are saying, because this is a smooth curve, which means 1 and 2, which means continuous and differentiable, there must be a point C where there is a tangent line parallel to the secant line. That's the concept. And that is the point C. This is AF of A, this is BF of B, and this is the point we are looking for. That's the concept. Somewhere in between. Okay. So f of B minus f of A over B minus A represents the slope of a secant line. So you have two pairs, come up with the slope. In other words, there is a point P where the tangent line is parallel to the secant line AB. So the mean value theorem, number one, f is continuous in a closed interval of a to b. Number two, f is differentiable on the open interval of a to b. Then there must be a number c in the open interval such that f prime is f of b minus f of a over b minus a. By the way, if you do the cross product here, please understand number one and number two are equivalent, okay? In other words, we could say f prime of c is f of b minus f of a over b minus a, or we can say f of b minus f of a is f prime of c times b minus a. They mean the same thing. And note, Rolle's theorem is a special case of the mean value theorem. When we add the third criterion that f of a and f of b are equal, what happens that if f of a and f of b are equal, it must be a horizontal secant line. Horizontal secant line has a slope that is 0, and therefore there must be a point where there's a tangent line with the slope of 0. That is the Rolle's theorem. So we wanted to make sure we understand the difference between the two. Given f of x is 5 minus 4 over x, find all c in the interval of 1 to 4 such that the slope of a secant line equals to the slope of a tangent line. This is a rational function. We should be able to graph it easily, and we'll discuss the graph at some point. And so we take it from there. In the meantime, 1 is here, 4 is here. At 1, if we plug in 1, by the way, if I plug in 1, I get 4 over 1, 4, 5 minus 4 is 1. So I hope you see that as 1, 1, just in case. And if I plug in 4, I get 1, 5 minus that is 4. So it's 4, 4. This one. Coordinates 4, comma, just in case. And so you connect them, and here's your secant line, and we are saying that there is somewhere in between that the tangent line is parallel to the secant line. So what is that point? That's what we are looking for. That's the question. I want to make sure that it is understood. So this is a rational function. And as you know, the domain of a rational function is all x except what makes the denominator 0. As you can see, x equals 0 makes the denominator 0. So you have to exclude 0. The domain is all real numbers except 0. Therefore, we're going to write f is continuous on -infinity to 0, union 0 to infinity, and it makes it continuous in the closed interval of 1 to 4, because 1 to 4 is part of this. 1 to 4 is part of that. And it's a smooth curve. A rational function is continuous in its entire domain, and it's differentiable in its entire domain. It makes it differentiable in the open interval of 1 to 4. So let's calculate f prime of c, which is f of b minus f of a over b minus a. So f of a 4 minus f of a 1 over 4 minus 1. And so I've calculated this for you, right? 4 minus 1 over 4 minus 1 is equal to 1, because the y coordinate, it so happened at 1, y coordinate is 1, at 4, y coordinate is 4. It happened to be the case. And so f prime equals 1. So all you have to do, set up f prime of x equal to 1, which means, let's calculate the derivative quickly. For this one, maybe I rewrite it as 5 minus 4 x to the power minus 1. So that is the function. And so f prime of x, let's just do it here and then we erase it. F prime of x was minus 4 minus 1 x to the power minus 2, which makes it positive 4 over x squared. You set that equal to 1. Cross product tells us x squared must be 4 and x must be plus minus 2. So there are two answers, everybody. -2 and +2. However, in the interval of 1 to 4, it's only 2. So why 2 only? Because in the given interval, it's 2. -2 works out the same class. At -2, we have another tangent line parallel to that, but we just want it in the interval of 1 to 4. I hope everybody's clear on that. So in other words, there is one more. But that's not what we are interested in, okay? Because it's not in the interval of 1 to 4. Suppose that f prime of x is between 3 and 5, inclusively for all x. Show that 18 is less than or equal to f of 8 minus f of 2 less than or equal to 30. All right, so to do so, the very first thing we notice, as far as the mean value theorem, this is like f of b minus f of a, and we are looking at this concept in essence. And if so, then A must be 2, B must be 8. So I'm going to claim f is continuous on the closed interval of 2 to 8, because A is 2, B is 8. And f is differentiable on the open interval of 2 to 8. Why is that? Well, take a look. Suppose that f prime of x is between 3 and 5 for all x. What does it mean? The function is differentiable because f prime is between 3 and 5. It indicates that it's differentiable everywhere. If it's differentiable everywhere, it's differentiable in the open interval of 2 to 8. And if it's differentiable, it's also continuous, not the other way around. Differentiability means also continuity. So the proof comes from the fact that this is given. Therefore, the mean value theorem applies, and we're going to work with the mean value theorem. If f prime is always between 3 and 5, then this piece, f prime of c, which is f of b minus f of a over b minus a, must be also between 3 and 5. So f prime is always between 3 and 5. So this must be between 3 and 5 as well. So what is a, what is b? We're going to use a equals 2, b equals 8. When we do that, we get f of 8 minus f of 2 over 8 minus 2. What is 8 minus 2? 6. Let's multiply all sides by 6. So when we do that, this becomes 18. This one, the denominator goes away. This one becomes 30. And that's exactly what we have here. We just proved that f of 8 minus f of 2 must be between 18 and 30. We just proved that, everybody. All right, 4.3 summary, how derivatives affect the shape of a graph. Theorem, a function is increasing where f prime is positive. A function is decreasing where f prime is negative, meaning if you look at this function, the curve almost looks like a line with a positive slope increasing, with a negative slope decreasing. A critical point C of a function is a point for which f prime is 0 or f prime DNE does not exist. A relative maximum or relative minimum is a critical point at the top or bottom of an interval of a graph. A function is concave up where f double prime is positive, f prime is increasing, looking like that, concave up, can hold water in essence, remember in pre-calculus. A function is concave down where f double prime is less than 0, f prime is decreasing, it can't hold water. And finally, an inflection point, C, is a point where concavity changes. Inflection points occur where f double prime is 0 or f double prime does not exist. As you can see here, for example, this is concave down, and it changes to concave up at this point. Where the change occurs, we have an inflection point. Concave up, the graph of f of x lies above all its tangent lines on the open interval. Concave down, the graph of f of x lies below all of its tangent lines on an open interval. For example, this is concave up. If you draw a tangent line, it's above it. The same thing here. This one is concave down. This one is concave down. If you draw any tangent line randomly, that means the graph is below the tangent line. Also, if we look at these two cases, what do we notice? If double prime is positive, means f prime is increasing, and that means concave up. want to make sure we understand what happens. If you look at this one, and we did a couple of tangent lines, both these tangent lines have a slope which is positive. But I hope you see this is steeper and it's therefore larger than this one. On the other hand, these two, both of them have a negative slope. And this is steeper, so this is more negative than this one. So F double prime is getting larger. That's the idea. F prime is increasing. F double prime is positive. F double prime is negative. That means F prime is decreasing. F prime is getting smaller. So F prime, which in this case, if you draw a couple of tangent lines, that means the slope of a tangent line at that specific point. Look at this one, negative slope, negative slope. But this is more negative, so it's decreasing. It's getting smaller, the slope. This one has a positive slope. This one has a positive slope, okay? And this is steeper. This has a positive slope larger than this positive slope. So F prime is getting smaller, okay? And finally, a point P on a continuous curve f of x is an inflection point if f of x changes concavity. Here's the example. Concave down, concave up, point of inflection. Concave up, concave down. This is the point of inflection. Extreme values of a function are created when the function changes from increasing to decreasing or from decreasing to increasing. So increasing, decreasing, the change occurs, creating an extreme value. This is a local max. First is decreasing, then it's increasing, creates an extreme value. That's a local mean. Decreasing, increasing, decreasing. This extreme value is a local minimum. This is a local maximum. Increasing, decreasing, increasing, decreasing. So this is a local max, local mean, local max. Therefore, the theorem indicates a function is increasing where f prime is positive and decreasing where f prime is negative. Now we can prove this by the mean value theorem, by the way. According to the mean value theorem, f is continuous on the closed interval of a to b and differentiable in the open interval of a to b, then f prime of c must be f of b minus f of a and over b minus a, and it's equivalent to saying f of b minus f of a is the product of these two pieces. In other words, f of b minus f of a is f prime of c times b minus a. Now here's the graph. You pick 2 points to connect them. It becomes a secant line. Again, you have a curve which is smooth. A smooth curve means differentiable and therefore continuous. So there's somewhere in between, in this case, point C, that you can draw a tangent line which is parallel to that. That's the idea of the mean value theory. And so, as I mentioned, we can rewrite this in this fashion. Now, what does increasing means? A short version of that is that increasing for a function f of x means when x gets larger, so does y. That's the meaning of it. As you know, we go from left to right. Obviously, x gets larger. So what happens to y? If the y gets larger also, that means increasing. If y gets smaller, that means decreasing. That's a very simple way of approaching that. So we are assuming that, of course, b is on the right side of a, and therefore b is larger than a. B is taken to be larger than a. If f prime is positive, f prime of x, that means this is positive. F prime of c, which is f of b minus f of a over b minus a, is positive. So if f prime of x is positive, f prime of c is positive, f of b minus f of a over b minus a is positive. And we said B is larger than A, so B minus A is positive. If the denominator is positive, the numerator must also be positive for the expression to be positive, right? Positive over positive is positive. So if B is larger than A, then f of B must be larger than f of A. And that is the definition, the simple definition of an increasing. X gets larger, Y gets larger. So anyways, now what is the first derivative test? Y prime or f prime is positive. That means curve is rising first. It's increasing. Y prime or f prime is negative. That means curve is falling. Then it creates an extreme value, which is a local max. On the other hand, if it's first negative, so first is decreasing, then Y prime or f prime is positive, curve is rising. Again, it creates a local extremum. In this case, it's a local minimum. And it happens where Y prime or f prime is zero or does not exist. That means critical points. And so those are possible local maximum or minimum, and you have to check it. How do you check it? Use sign graph for this test. We will look at that later on. Test of concavity or concavity test. Y double prime or F double prime is positive. That means curve is concave up. Y double prime or F double prime is negative. That means the curve is concave down. When it's zero, Y double prime or F double prime, or it doesn't exist, that would be possible inflection point where concavity changes. In this case, concave down, concave up. That's the change. A function is concave up where f double prime is positive. That means f prime is increasing. A function is concave down where f double prime is less than zero, negative, or f prime is decreasing. And obviously, we use the sign graph for this test as well. Now, we don't want to mix this up with the second derivative test. Second derivative test gives you half of the information of the first derivative test. And so for the graphing, always we use the first derivative test, but this is a good test for applications. Evaluate f double prime at CPs. In other words, first find f prime, find the critical points by setting it equal to zero or does not exist, then plug it into f double prime. So when you do that, what happens? If it's less than zero, then the graph is concave down looking like that, then it must be a local max. On the other hand, if it's positive, graph is concave up, looking like that, this must be a local minimum. The second derivative test can tell you whether a critical point represents a local max or local. Now, we are almost ready for graphing, but just to make sure we are in good shape, I am going to remind you of what we have learned in algebra, college algebra, pre-calculus, you name it. The end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. So a polynomial function f of x is a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 all the way to a sub 0. And this is called the leading term, which means as x gets larger and larger, ultimately this will take over. And the shape depends on this piece. So if we have a sub n, the leading coefficient to be positive, and if the power n is even, it either looks like y equals x squared or y equals negative x squared. So if a sub n is positive, it looks like f of x equals x squared. If it's negative, looks like f of x equals minus x squared. In this case, x approaches negative infinity, so does so f of x or y approaches positive infinity. That means the third quadrant, the second quadrant. X approaches infinity, so does y. That means the first quadrant. On the other hand, whether x approaches negative or positive infinity, f of x or y goes to negative infinity. That refers to the third and fourth quadrant. Now, if we are dealing with odd power, in other words, we are dealing with this case where n is odd, then it will look like either x cubed or minus x cubed. If a sub n is positive, looks like x cubed. If a sub n is negative, looks like minus x cubed. In the case of a x cubed, we are looking at the first and the third quadrant, meaning x goes to negative infinity, so does y. Remember, f of x is y. X goes to infinity, so does y. So first and third quadrant. On the other hand, if a sub n is negative, x goes to negative infinity, y goes to positive infinity. X goes to positive infinity, y goes to negative infinity. So looking like minus x cubed. I hope everybody remembers that as far as graphing. The other theorem is behavior near a zero. It depends on the multiplicity of the zero. X minus c to the power of m as a multiplicity m. If m is odd, f crosses the x-axis at c0. If it's even, f does not cross the x-axis. It bounces back. So for example, here, just single, that means odd, number one. This one, multiplicity 2, even as it hits it, it has to bounce back. This one crosses because, again, this is odd. The only thing you want to remember, the higher the multiplicity, the flatter the curve is at the zero. The sum of the multiplicities is the degree of the polynomial function, namely n. So a lot of information. It's a lot of information from algebra. I hope it's coming back to you. If not, you can check it out. You can also ask me for resources. All right, here's a graph we want to do. Graph f of x equals minus x cubed plus x squared plus x. And of course, it explains how to do it, but it says steps to curve sketching in addition to algebra pre-calculus. So what I'm going to do, I'm going to ignore this, and I'm going to use algebra pre-calculus to graph it as we did before. I want to show you how it works, okay, everybody? And then we add calculus. So to do so, I'm going to refer to the fact that I know this one looks like minus x cubed as far as the end behavior is concerned. So this, again, I'm not going to pay any attention to calculus yet. This tells me about the end behavior, which means this, which means the second and the fourth quadrant. And then I'm going to find the intercepts and take it from there. To find the intercepts, I'm going to factor the negative x out. If I take the negative x out, I get x squared minus x minus 1. The reason I take a negative x out, because I want to see if I can factor this. I can't. So I'm going to use, so minus x times x squared minus x minus 1 equal to 0. So I'm going to use the quadratic formula, okay, to come up with the answer. For this part, okay, A is 1, B is -1, C is -1, plug in. Okay, and minus B minus minus 1 is 1 plus minus the square of B squared minus 1 quantity squared minus 4A times C over 2 times A, 2 times 1. And we get 1 plus minus square root of 5 over 2. So first of all, this gives us 0, 0. Then this gives us 2. We have the following 0, 0, 1 plus square root of 5 over 2, 1 minus square root of 5 over 2. Okay, so we have all the intercepts. By the way, 0, 0 happen to be the y-intercept as well. If not, set the x equal to 0 and find the y-intercept. That's a good point to know. And to have the graph square root of 5, we should know it's roughly 2.5. 2, 2.3. And so when you work on this, this is 0, 0. This becomes, again, for the sake of graph, roughly 1.6 or 1.620. This one becomes negative 0.60. This is for the sake of graphing. So this is 1, this is 2. Negative 1, negative 2. 1, 2. All right. So obviously we have 0, 0. Then we have 1.6, so somewhere here, 0. And then we have negative 0.60, somewhere here. None of them is to scale. So the graph, so we start from the second quadrant. We hit this first 0 we come across. It has to come back up. We may not know at what point, but it has to come back up. Then it has to go back down to hit the last 0. And of course, it crosses each and every one of them because each one has a multiplicity 1. This has multiplicity 1. This has multiplicity 1. And this. So this is the graph. So you're in good shape. You used algebra. You can graph it. You're done as far as prior knowledge of mathematics is concerned. However, when we add calculus, we can find relative max and mean and intervals where the function is increasing, decreasing. So we're going to set f prime of x equal to 0 and solve it. Then we go with the inflection point, set f double prime equal to 0 and so forth. So first, we are going to add this part, which means I'm going to erase my work. And I'm going to start with CPs, critical points, that means f prime. So I'm going to go back here and say negative 3x squared plus 2x plus 1. And I want to set this equal to 0. To do so, I'm going to factor. To do the factoring, I'm going to take the negative out. And because three is a prime number, we have 1x and 3x. And negative 1, we have no choice but to go with 1 and negative 1. But where do you put it? Well, if I put it here in this format, I have to check. The product of these two is negative 3x. The product of these two is positive x. Do these add up to negative 2x? Yes, that works. That's how you factor. I hope everybody can see it's elementary algebra. And so again, I'm going to erase my work. This is 0x is 1. This is 0x is negative 1/3, everybody. So we go with the first derivative test, which means we are going to go with a number line from negative to positive infinity. X negative to positive infinity, we put these two numbers in order from smallest to largest. Negative 1/3 f prime is 0. Positive 1 f prime is 0. And now we have to see what happens here, here, here. And that means you pick up a TP, short for test point. So the test point to the left of negative 1/3 would be like negative 1, in between would be 0. After that would be maybe 2. Again, just make up any number you want. The easiest one is 0. Before we continue, I want you to notice f prime has degree 2 and has two answers. So they must alternate because each one has an exponent 1. It's an odd exponent. So the easiest one, you can actually do the work. Plug in 0 into this one or this one, doesn't matter. If I put it here, I get +1, so it's plus here. If it's positive and they alternate, they must be negative. If you have doubts, just plug in, let's say, -1 and observe +2 and observe, you see that. But because it's important to understand when and how they will alternate, okay? Again, degree 2, two different answers, they must alternate. So To have a better understanding of this, okay, I'm going to throw in arrows. This means decreasing, negative decreasing, positive increasing, up arrow, decreasing. So it gives me a lot of information here. So it's decreasing here, increasing here. As we change from decreasing to increasing, this is the point where we have a local minimum. As it changes from increasing to decreasing, this is where we have the local maximum. And let's put it back into the original function. If I put the 1 here, negative 1 cubed plus 1 squared plus 1. I hope you see the answer is 1, which means local maximum equals 1 at 1 comma 1. What about local minimum? Local minimum at x equals minus 1/3. But you need to have the both coordinates. So you have to put it back into the original function and evaluate. So f of negative 1/3 is minus negative 1/3 cubed plus negative 1/3 squared minus 1/3. This is negative 1 over 27. This makes it positive 1 over 27. This is positive 1 over 9. This is minus 1/3. The common denominator is 27. This is 3 over 27. Minus 9 over 27. That means 1 and 3, 4 minus 9 is negative 5 over 27. That means local minimum is equal to this number at the pair negative 1/3 and negative 5 over 27. As I mentioned, look at up arrow or positive, increasing from negative 1/3 to 1, decreasing from negative infinity to negative 1/3 union 1 to infinity. So the first derivative test will give you all the extrema, local max, local mean, where the function is increasing, where the function is decreasing. It gives you a lot of information. All right, so we did the first part, everybody. Now we want to go to the second part. So first, I'm going to write everything from the previous page. Here's the function. Here's the f prime that we found. Here's the intercepts that we found. Here's the maximum. Here's the minimum. Here's where the function increasing, decreasing. So this is just information from the previous page. And now I want to go to f double prime. So to find IPs, I'm going to go to f double prime. So what is f double prime? Negative 6x plus 2. You set this equal to 0. I hope everybody is okay with that. That becomes simply positive 1/3. You go with the sign graph again. The sign graph goes from negative to positive infinity. You put this number there and you say when x is 1/3, f double prime is 0. So you pick up a test, and there's only one answer, and this is degree 1, so they will alternate. So you pick up a number to the left. I'm going to call it again TP, test point. To the left of 1/3, the test point would be, for example, 0. To the right would be 1. Those are easy numbers. So if I plug in 0 into f double prime, I get positive 2. So positive, this one is negative. But they alternate. If you have doubts, put 1. You get negative 4. So because of the change, this is the point of inflection. Because this is positive, it's concave up here from negative infinity to 1/3. Because it's negative here, it's concave down from 1/3 to infinity. And to find the y coordinate of the inflection point, the x coordinate is 1/3. The y coordinate, you put it back into the original function and evaluated everybody. So negative 1/3 to the third plus 1/3 squared plus 1/3. So minus, this is 1 over 27. This makes it negative. Negative 1 over 27. This is 1 over 9. This is 1/3. And again, the common denominator is 27. Let's see if I can put it here, 27. This one is negative 1. This one is 3 over 27. This one is 9 over 27. So 9 and 3, 12 minus 1, 11 over 27. So the IP, the inflection point, has the coordinates 1/3 and 11 over 27. So we have just about everything we want. I like to summarize the information here. This is nothing brand new. We've done all of this. So the x-intercept is at 0, 0. Another one, precisely 1 minus square root of 5 over 2. I'm going to change it to negative 0.620. Another one, 1 plus square root of 5 over 2, 1.620. The maximum at 1, 1. The IP address, 1/3 and 11 over 27, let's say 0.33 and 0.41. Again, this is for the sake of graph. And the minimum at negative 1/3, negative 5 over 27. This is the decimal representation. And we are going to start graphing. Let's start with 0, 0. Negative 0.6. This is negative 1. So somewhere here, negative 0.62. 1.62. This is 1 somewhere here, 1.62. Then we have the maximum at 1, 1. Now, when it comes to maximum and minimum, you always put an arrow, a double arrow, meaning when the function gets there, it has to bounce back. It can't cross. That's the meaning of double arrow and maximum or minimum. Now, the IP address, we're going to go with the decimal 0.3 and 0.4. So 0.3 and 0.4, somewhere there roughly. Okay. And the minimum, negative 0.3 and negative 0.2, somewhere there. And again, maximum as well as minimum, double arrow, meaning it can't cross. We discussed the fact this means the end behavior is in the second and fourth quadrant. So we graph it, we get to the first 0. As it hits the minimum, it bounces back. Second 0 goes through that, this one, and the graph looks like that. And I hope you can see what's happening here. We have all the zeros. We have the max, we have the mean, and notice the function is concave up. And at the IP address, it changes, becomes concave down. So everything that we did with usage of calculus makes the graph look more precise. That's the bottom line, everybody. All right, example 33, f of x equals half of x to the power of 4 minus x squared. And we want to graph this again. I want to graph this using prior knowledge of mathematics. And so we are going to find the intercepts and so on. So f of x equal to 0, 1/2 x to the power of 4 minus x squared equals 0. We can factor out either x squared or half of x squared, makes no difference. Half of x squared comes out as x squared minus 2. I hope you realize This means x is 0. And this means x squared equals 2, and x is plus minus square root of 2. So the intercepts, and it's a good idea to write them as pairs, 0, 0, negative square root of 2, 0, positive square root of 2, 0. So we have those intercepts, intercepts. The first one, let me erase my work. The first one is both x intercept as well as y intercept. So if we were to graph it just the way we have this, here's 0, 0. Square root of 2 is about 1.41, roughly 1.4. Somewhere here, and negative 1.4 somewhere here. When we look at this one, the leading term, half of x to the power 4, the exponent n is even, and 1/2 is positive. So it looks like y equals x squared, the n behavior. Number one. Number two, when we look at the zeros or x-intercepts, this one, that means two of them, so each one is having exponent 1, or it's odd. This one has exponent 2, so 0, 0 has multiplicity 2. They use m to represent multiplicity. So that means graph can't cross that. So that's why I'm going to use the double arrow. So now if we just stick with that, the graph looks like this. It hits the first x-intercept. It has to come back up at some point. We may not know when. And it hits the second one, but it can't cross. Has to come back down again and then come back up. This one can cross. The other thing that is helpful when you graph with prior knowledge of mathematics would be odd and even. You can calculate f of minus x. You see that it's equal to f of x, which makes it an even function, which makes it symmetric with respect to the y-axis. The right half and the left half look the same. So that would be helpful. And of course, you can pick more points. In other words, we could graph it, but with calculus, we know exactly where the local max and mean is, and that inflection points, that makes it look a lot better. That's the idea behind that. So having said that, I'm going to erase my work and I'm going to continue working with calculus, finding extremum, meaning I have to go with f prime of x. So let me erase my work. So I'm going to go with f prime of x. To do the first derivative test, I'm going to go with f prime of x. So that means 1/2 times 4, 2x cubed minus 2x. And to set this equal to 0, I'm going to factor the 2x out. When I factor the 2x, I get x squared minus 1. And this would be 2x times x plus 1x minus 1. There are 3 zeros. X is 0, x is negative 1, x is positive 1. So there are 3 answers. Now, please understand this f prime has degree 3 and has 3 answers. Therefore, when we go with the number line, we're going to put those numbers in order. From negative infinity to positive infinity, these 3 numbers, negative 1, 0, 1, f prime of x is 0 at each case, and they will alternate because each one, this one has exponent 1, this one has exponent 1, this one has exponent 1, exponent odd. Even if it's 3, it would be the same. But for the sake of argument, let's say this has exponent 2, then both sides of this number, which is 1, they would have the same sign. Okay? Because it's odd, they will alternate. So as far as TP is concerned, what would you pick as a TP to the left of, let's say, -1 would be -2. Between -1 and 0, let's say -1/2. Between 0 and 1, the test point would be 1/2. Beyond 1, let's say, is 2. But like I said, you don't have to check each and every one of them. Just check one of them. For example, if you put 2, and you can put it in either in this format or in this format, it makes no difference. But whatever it is, if I put it here, 2 cubed is 8 times 2 is 16, minus 4 is 12, becomes positive. If this is positive, they will alternate positive, negative, positive, negative. And I'm going to erase my work and the TPs. And I'm going to throw in arrows, down arrow for negative, up arrow for positive. This means decreasing, increasing, decreasing, increasing. So that tells me where the function is increasing, decreasing. Also, it gives me the local extrema. So decreasing to increasing, this is a location of a local minimum. Increasing to decreasing, location of a local maximum. Decreasing to increasing, location of a local minimum. So we have 2 of the minimums and 1 of the maximums. So as far as 0 is concerned, of course, we already have 0, 0 if you plug in. So that is not only an x-intercept, not only a y-intercept, also the location of a local max. In other words, local max is 0 at 0, 0. But what about local mean? We are going to put -1 into the original function. But because of the format, if I put +1 also, it gives me the same answer. So I'm going to do it at the same time. So whether it's +1 or -1 to the power of 4, this is 1. So we are looking at 1/2. And the same thing is 1, so -1. 1/2 minus 1 gives you -1/2. So that means local minimum is equal to -1/2 at 2 different points. And we're going to write the pairs, -1 comma -1/2, +1 comma -1/2. 0 was already discussed, and that means 0, 0. Again, 0, 0 is the x-intercept, the y-intercept, the local max, all of the above. Now, where is the function increasing from -1 to 0? Union 1 to infinity. Where is the function decreasing, negative, from -infinity to -1? Union 0 to 1. We write that. So we have all the intercepts, increasing, decreasing, local extrema. And now we are going to go to the next part, finding the inflection point. First and foremost, I'm just writing the function, the information from the previous page we found, and f prime. I'm not writing anything else, class, okay? All right. So why am I writing that? So I can go to f double prime, which is 6x squared minus 2. To find the IP, I'm going to set this equal to 0. I can factor the 2 out, 3x squared minus 1. And if I set 3x squared minus 1 equal to 0, I want to just show you. If you set 3x squared minus 1 equals 0, that becomes 1. X squared becomes 1/3. And x becomes plus minus 1 over square root of 3. And so those are the inflection points. I'm going to go with the number line from negative to positive infinity. So possible inflection points at x equals plus minus 1 over square root of 3. So I'm going to put negative 1 over square root of 3 here. F double prime is 0, positive here, 0. And I'm going to do the test mode. And again, take a look at F double prime is of degree 2 and it has 2 answers. So they will alternate class. So the TP to the left of negative 1 over square root of 3, I hope you see you can use negative 1 in between. The easiest one would be 0. And to the right of 1 over square root of 3 would be 1. So go with 0. If you plug it into F double prime, everybody, F double prime makes it negative 2. So if this is negative, they will alternate. Both of them are positive. Because of the change from positive to negative, from negative to positive, both points are points of inflection. And over here is concave up, over here is concave down, over here is concave up, meaning you're going to say concave down from negative 1 over square root of 3 to 1 over square root of 3, concave up from negative infinity to negative 1 over square root of 3 union 1 over square root of 3 to infinity. So that's the first part. Then we want to evaluate the function at those points to get to the y coordinate of the IP. So plug in. And again, it doesn't matter which one you plug in. We're going to plug in both of them, plus minus, into the original function to find the y coordinate for each IP. So I'm going to start with this. When you raise this to the power of 2, 1 becomes 1. Square root of 3 comes out, becomes 3. So this is 1/3, everybody. So the power of 4 must be 1 over 9. So again, this is 1/3, so this must be 1 over 9. So if that's the case, this is 1 over 18. This is 1 over 3. That means 6 over 18 minus 6 over 18. Let me erase my work. 1 minus 6 is minus 5 over 18. So IP is at x equals plus minus 1 over square root of 3 because the concavity changes. This is the precise location. We write this as an approximation for the sake of graphs. So let's do the summary, everybody. So here's the summary. I want to make sure that everybody's okay with that. The x-intercept at negative 1.410, positive 1.410, 0, 0. The IPs, and we wrote those. The minimum at plus minus 1, negative 1/2. So let's start with, okay, so this is 0, 1, 2, negative 1, negative 2. So negative 1.41 is somewhere here. Positive 1.41 is somewhere here. 0, 0 is here. And for 0, 0, because it's also a maximum, we put the double arrow, meaning when it hits it, it can't cross when the graph hits it. Then we go with the IP address, negative 0.6, let's say negative 0.3, so here and here. Positive 0.6, somewhere here and here. Minimum and maximum. Here's negative 1. Here's negative 1/2. Okay. And we put the arrow, right? Because it's a minimum. Now, positive 1 is here. Okay. And negative 1/2. Again, we put an arrow. And as I've mentioned, this one is the leading term. The graph looks like y equals x squared. So first and second quadrant. So starting from the second quadrant, for example, you hit this and it crosses. You hit this one, can't cross. You hit this one, you hit this one, can't cross. This way, and that's the graph. Now notice, This is the local minimum, this is a local minimum, this is a local maximum. The function is concave up until it hits this point, which is the IP, concave down until it hits this point, concave up. The function is decreasing, increasing, decreasing, increasing. Everything that we discussed as far as calculus is concerned, we can see it here. Now we want to graph f of x equals x minus 2 to the power of 2 thirds plus 1. Again, I want to go with the prior knowledge of mathematics, pre-calculus, algebra, college algebra, and we want to graph this without paying any attention to calculus yet. So first and foremost, we're going to rewrite this as the cube root of x minus 2 to the power of 2 plus 1. This is ultimately a cube root, and we start with y equals cube root. We should know it's one of the elementary functions. We should know the graph looks like that. And of course, this is 0, 0. So that's the first one. Then we are going to go to cube root of x minus 2, which is the same function, but shifted to the right by 2 units. So shift right by 2 units. We're going to move this to the right by 2 units. And the effect of that is that 0, 0 moves to 2, 0. The next one is to raise this to the power of 2. So what is the effect of that when you raise some function to the power of 2? If you look at this blue graph, the positive portion just gets larger because it's being raised to the power of 2. The negative portion becomes positive, flips over with respect to the x-axis, and of course, in an absolute value sense, it becomes larger. And so what happens is that this keeps at the same location 2, 0. Finally, plus 1 means move it up by 1 unit, shift up by 1 unit. So this blue one, which became the green one, now moves the green one up by this much, by 1 unit. And therefore, 2, 0 moves to 2, 1. That's a graph. It has, been transformed, and the transformation has given you all the information you need. We are done as far as pre-calculus skills. What I want to do, I want to add to this other things. Of course, the concept of intercept, I haven't checked it here. We should. We will look at that in a moment. But let's go back to calculus and see what we want to do. We want to start with the first derivative test, which means we are going to differentiate everybody. So to differentiate, we're going to use this one. 2 thirds x minus 2 to the power of 2 thirds minus 1, which is negative 1 third, times the derivative of the inside, which is 1. You take the negative 1 third down, becomes positive, and you make it into a cube root. So to find CPs, you find f prime equal to 0, f prime doesn't exist. So f prime equals 0 doesn't give you any solution. Why is that? A fraction is 0 when the top is 0. The top or the numerator is a number, can never be 0. So there is no solution. F prime DNE does not exist. That means this must be undefined. A fraction is undefined when the denominator is 0. As you can see, the denominator is 0 if x equals 2. So there is one critical point. So what you do, you go with the number line from negative to positive infinity. You put this number, and at this point, f prime DNE does not exist. So you look at a test point to the left of 2, of course, the easiest point, I'm going to call it TP, let's say 0, and to the right is 3. So if I put the 0 into f prime, 0 makes this negative 2. Cube root makes it still negative. 2 and 3 are both positive, so the result is negative here. And they will alternate. You can check it out. If you put 3, it becomes positive. So what does that mean? Let me erase my work and throw in the arrows. That means the function is decreasing from negative infinity to 2, then arrow up, increasing from 2 to infinity, and this is the local minimum. We don't have a local maximum. So if this is the location of a local minimum, you have to put it back into the original function to find the y coordinate. So if I put 2 here or here, it doesn't matter. If I put the 2 here, it becomes 0. I hope you see that. Cube root is 0, square root is 0, so you get 1. So local minimum equals 1 at x equals 2. Again, how did we get the 1? Put the 2 into the original function. There is no local max. And as I mentioned, negative means decreasing here, negative infinity to 2, increasing here. So decreasing from negative infinity to 2, increasing from 2 to infinity. All right, so far so good. The next step is to find inflection point or IPs, which means you have to find f double prime. You have to differentiate it again. So to differentiate it, I'm going to go back to f prime here. And to differentiate that, okay, to find f double prime, I'm going to write here 2/3 times negative 1/3 x minus 2 to the power of negative 1/3 minus 1 times the derivative of the inside, which is 1. So we get negative 2/9 x minus 2 to the power of minus 4/3. I'm going to take this down, make it positive 4/3, and I'm going to write f double prime is negative 2/9 cube root of x minus 2 to the power of. Now notice, if you look at the denominator, is 0 when x equals to 2. So it can't be 2, but other than 2, because this is exponent for any number you choose, this x cube root becomes positive, negative, it doesn't matter. This makes it positive, 9 makes it positive, negative 2 makes it always negative. This is always less than 0, except when the denominator is 0, the expression is undefined, and that would be when x equals 2. So x can't be 2. So it's always concave down. But how do you write that? You don't write it as negative to positive infinity. You write it from negative infinity to 2, union 2 to infinity. And that's important because 2 is not part of the domain for f double prime. Okay. Now, you could do the sign graph. You don't need to. If you see that, you don't need to. But if you don't see it, let me quickly show you. So f double prime equals 0 because the numerator is a number. The answer is no. F prime doesn't exist. The answer is 2. You do the number line. Okay. Again, we do the same thing as here. To the left of 2, you pick a number. For example, 0. If I put 0 here, becomes negative to the power of 4, positive, positive. This makes it negative. If I put a number to the right of 2, for example, 3 makes it positive. The denominator is positive, but this makes it negative. So both sides are negative. If you don't see this one, you may have to do that. But as I mentioned, really, I hope you can see this and you don't have to worry about that. Okay. So that's pretty straightforward, everybody. Now, first, I'm writing the function and the increasing, decreasing, the minimum that we got. We also need to find the intercepts. So how do you find intercepts? Well, if you replace the x with 0 here, everybody, you get minus 2, squared, you get 4, cube root of 4 plus 1 is an exact answer. And cube root of 4 plus 1 is roughly 2.5874, let's say 2.6. What about the x-intercept? We don't have any. How do we know that? Set this equal to 0 and solve. In order to solve this, I'm going to move the plus 1 to the other side and I get -1. Then I'm going to raise both sides to the power of 3 because the denominator of this piece is 3. I'm talking about this one, everybody. So we have x minus 2 squared equals -1 cubed equals -1. This is being squared. How can it be a negative number? Never, ever. There is no solution. So we don't have x-intercepts. And of course, you're going to graph it. To graph it, we can use other points, okay? So first, let me give you the summary of the points we have. We have the y-intercept. We have the minimum, but we really need a couple of easy points, and I'm going to show you how to find those easy points. For example, if I put 1, if I pick 1 here, it becomes -1. Cube root of -1 is also -1. Square it, +1, and 1 is 2. I hope you see that it's 1, 2. Another easy point would be 3. If I put 3 here, I get 1. Cube root of 1 is 1, squared is 1, 1 and 1 is 2. Okay. If I pick, for the sake of argument, if I pick 10 here, 10 minus 2, 8, cube root is 2, square is 4, and 1 is 5. So you can figure this out. These 3 points, this one, I'm using this one to show you, well, I can calculate it, I use a calculator. But for -6 and 10, you can also, I showed you the 10, -6 becomes -8. Cube root is -2, square root is 4, and 1 is 5. So now let's plot those points that we have. So to do so, we start with the very first point, everybody. And so the first point, cube root of 4, we're going to go with 2.6. Let's say this is 1, 2, 2.6, somewhere here. Okay. This one is 1, 2. This one is the minimum 2, 1, 2, 1. Uh, 3, 2, 3, 2. This is the minimum, 3, 2. -1, 3.08. -1, 3.08. -6, 5. So -6, 5. 10, 5. Put them together. And notice the function is decreasing here. The function is increasing here. Clearly, it shows that. The function is concave down here. The concave is concave down here. It clearly shows that.